Hey y'all, and welcome to the first lecture in the Practical Packet Analysis course. My name's Chris Sanders, and I'm really excited you're here, and I'm thrilled to get started teaching you about the practical aspects of performing packet analysis. This first lecture is called Packet Analysis and Network Basics. In this module, we'll start by defining what a packet is. So that's kind of the core thing we're working with here, and we want to understand exactly what constitutes a packet and where we might encounter one. So we'll talk about what that is and also what it means to actually analyze packets. So specifically, why would you want to do that? What benefits are you going to get out of it? How is it going to help you in your daily job, maybe as a network administrator or as a programmer or as a security analyst? There's a lot of ways packet analysis can help you, and we're going to talk about a few of those. We're going to start as well by talking about some networking basics, and we really want to frame that through something called the OSI model. So we'll describe the OSI model and how that can be used to describe a lot of the network-based things we're talking about as kind of a frame of reference. Finally, we'll talk about network communication, and this isn't meant to be an all-encompassing view of how computers communicate on the network, but it is meant to extract the practical aspect of that so you can, at a high level, really understand what is happening when computers talk to each other and how things like protocols are used to govern that communication. So why would someone want to do packet analysis? What can you accomplish with it? First of all, packets are really the fundamental building blocks of network communication, and we'll talk a lot more about how that works and how to conceptualize that as we go along. But really in anything, if you want to understand the thing you're looking at, you really want to break it down to those fundamental building blocks so you can understand what's happening at a very basic level and kind of build from there. It's that whole approach of bottom-up processing or bottom-up learning, and that's what we're really doing with packet analysis, is taking that fundamental approach. Now, of course, this course is really focused on a practical view on that fundamental approach, so we're not getting really in the weeds. We're not going and digging really deep into protocol specifications or looking at a lot of binary data in a lot of cases, but that's okay because this is really about kind of extracting the absolute necessary practical things you need to get the job done and equipping you with the knowledge to go forth and seek additional information as necessary. Another reason you would do packet analysis is because at the packet level, there are often very few secrets. Generally speaking, when you're talking about two devices communicating with each other, whatever they're saying to each other is going to be found in the packets. Now, that's not to say that the packets might be obfuscated or encrypted of some way and might prevent you from seeing what you want to see, but the data is there. So if you're a programmer and you're troubleshooting why your application is not doing what it's supposed to on the network, you will have some evidence of what that is, and it's your ability to interpret that that's going to allow you to effectively troubleshoot. The same goes for network administrators or systems administrators who are troubleshooting connectivity between devices. The answer will be there. It's just your ability to analyze it. Furthermore, if you're a security analyst, it's oftentimes that the only evidence you'll have of a network attack is the packets that are collected representing the attacker's connections and activity related to your internal network hosts. So not a lot of secrets at the packet level. Really often the only thing standing in between your ability to get the answers you're looking for is the ability to analyze packets and understand what's going on at that fundamental level. Finally, there's a lot less abstraction from the data you're dealing with at the packet level. The simple truth of the matter is that applications often lie to us in terms of what's happening with the data. So many times an application may say, oh, hey, I'm not receiving any data. Whereas at the packet level, you can actually see that the application is receiving the data, when in fact, maybe there's just an unhandled exception. There's a reason that program doesn't know how to deal with the data it's getting. Maybe it's formatted improperly, things like that. When you're less abstracted from the data and you don't have to rely on user level applications to tell you what a problem is, you can actually make better decisions about what problems may be occurring and how to best troubleshoot that. So these are all reasons why you would want to perform packet analysis. Again, it's a fundamental building block. There are very few secrets at the packet level, which is a really great thing. And anytime you can be less abstracted from the data you're dealing with, you're going to be ultimately much better equipped to assess problems and understand what's going on. So what specific tasks can you do with packet analysis? How is it actually going to help you in your day-to-day job? Well, first of all, it's really going to help you understand your network. Oftentimes, the only thing standing in between you and solving a problem is having a deep knowledge of how communication works on your network, particularly what's normal for a device. Because if you can understand what's normal, you can ultimately have a better chance of understanding what's abnormal. If a system communicates using a specific traffic pattern and there's a deviation from that pattern and then there's a problem all of a sudden, then you might be able to figure out maybe what changed. What was the thing that changed either within the operating system or within an application, something like that. Beyond that, the ability to troubleshoot errant and slow communication is going to be really important, especially if you're a systems or network administrator. I think we've all been told at some time in our careers, and maybe for some of us every single day, that the network's slow. If you work a ticketing system, I'm sure you've gotten many tickets before that say the network's slow. And packet analysis is a really great way to troubleshoot that slow and errant communication, particularly to, I'm going to say pass blame, because oftentimes if you're the network admin, everyone wants to complain the network's slow, when more often than not, it's not the network that's slow. It's actually an application on the network or an individual system or something like that. So figuring out where the source of the problem is often half the battle. And if we can eliminate the network or focus in on a specific host or a specific application, that really helps a lot, and that's going to help both please our users, please our bosses, and help us better organize our time so we can focus on things that really matter and keeping the lights on, so to speak. So that's very, very helpful. Beyond that, just fixing problems, right? And if you can do the first thing of understanding your network, being able to identify the source of a problem, being able to tactically execute a plan to fix that problem is a very great thing. Granted, you may not have a lot of network problems in your day-to-day. Maybe you you have a very static network that doesn't change a lot. But if you do decide to add some network segments or reconfigure some things, maybe you reconfigured some routes on a router, or you moved a host from one network to another and things aren't communicating properly, the ability to look at packets and see what's going on at the packet level, applied with a fundamental understanding of how common protocols like TCP and IP work, are really going to equip you well to trace down the source of problems when the operating system or application you're dealing with maybe doesn't provide the most detailed of error messages. Operating systems and applications can't possibly be configured to account for every single scenario of what they might see on the wire. So it's not totally reasonable to expect them to be able to report accurately everything they're seeing. So being able to perform packet analysis can help bridge that gap quite a bit. Packet analysis is also incredibly useful if you're a security analyst. Maybe you do network forensics or incident response, or you're interested in moving into those fields. Packet analysis is one of those core skills that really anyone in defensive or offensive security needs to possess. Oftentimes, attacks are network based, and generally anytime an attacker comes into your network, unless it's physically, there's going to be evidence of their presence on the network. So whether that's the attacker themselves directly connecting into a system, maybe using stolen credentials, or they're using some type of malware and there's some type of malware command and control sequence going on. Oftentimes you'll be able to identify this using packets. Even when it's not you doing this identification, perhaps you have an intrusion detection system, something maybe open source like Snort or Suricata or Bro or something of that nature. When you get an alert from a network-based IDS, the data that's provided to help you clarify if an attack actually happened is going to be network-based data. It's going to be packet data. So the ability to analyze those packets in relation to the signature that alerted you is critically important. And it's one of the fundamental baseline skills that any security analyst needs to have amongst many others, but it's certainly one of the most important. So for all these reasons, there's a whole lot you can do with packet analysis, and we're going to start in this course with a lot of fundamental knowledge to build you up to the point where you can do a lot of these things. And then later on in the course, we're going to look at a lot of specific scenarios and examples related to all of these things, both understanding your network, troubleshooting errant slow communications, fixing problems, and identifying attacks. So what is a packet? Well, without further ado, we have one on the screen here. So this is it, right? This is all you need to know. This is a packet. This makes sense, right? You know what's going on here? Well, okay, maybe this isn't the easiest thing to understand. Let's talk a little bit more about what a packet is and how packets are made. Ultimately, a packet is just data from multiple protocols that is encapsulated and transmitted from one networking device to another. That's the formal definition that I really like to use for a packet. The more simplified definition would be it's just a bunch of data that's transmitted between devices. But this is a little more formal, and there's a lot here, right? There's a lot to kind of unpack if you don't understand what these individual things mean. What's a protocol? What's it mean to encapsulate something? What necessarily quantifies a networked device? And so on. So let's dig into the different parts of this to kind of build this foundational knowledge of what a packet is and how computers communicate and how packets play into that. Now, I mentioned protocols, so let's start by talking about protocols. And I want you to think about this in terms of problems and solutions. In this case, the problem is that when you're developing computers and when the internet and network communications are just starting to become a thing back quite some time ago, you had all these different systems, all kinds of vendors. You had IBM, you had non-IBM, all kinds of different operating system platforms, all these different things. But the idea is that they all needed to be able to talk to each other. Right? So how do you take these things that are fundamentally different in how they're designed and how do you allow them to talk to each other? Well, the answer is what we think of as our standard protocols. A protocol is really nothing more than a set of rules that governs how devices communicate with each other. Right? And so the idea is that no matter what system you're running on, whether you're on an IBM or non-IBM compatible system, so on and so forth, they're all using the same protocol to write code that will allow network devices to communicate with each other in a seamless way. That's why I can be here on a Mac and communicate with someone who's using a Windows device or a Linux device, or how I can even communicate with non-traditional things. I can communicate with my toaster that has an IP address for remote management. My toaster doesn't really have an IP address, but they do sell those. So your Internet of Things devices can also have these same protocols being used, their own implementation of them, of course, but they're using these protocols to allow this type of communication. So that's a really important thing to consider, is that interoperability here. Now, protocols, just like a spoken language, are the language computers use to communicate. So when you think about a human language, you might think of, let's think of English, right? A person might say hello and another person might say hello back or hi there. There's a lot of different ways to say hi, but there are some generally accepted rules for what makes up spoken words, right? There's words that mean a greeting, words that mean farewell. There's verbs and nouns and adverbs, and they're all structured in specific ways. So we have this concept of language, human language, which allows us all to speak and to understand with each other. Of course, we have multiple languages in the world, but the idea is that by implementing or learning a certain language, you can speak with all the people who can speak that language. And the idea with network protocols is really the same type of thing. It's that anybody who wants to speak to all these other devices that are speaking TCP/IP, if you also implement TCP/IP based upon the specification of what that should look like, then you can also communicate governed by those same rules. In this sense, we have, a TCP greeting. So we'll talk about transmission control protocol in detail later, but what we have on the screen here between computer 1 and computer 2 is really the same thing that we have with our English greeting between person 1 and person 2. Computer 1 says sin, computer 2 says synac, and computer 1 says ac, and that's basically the equivalent to a greeting. So when we're talking protocols, remember, we're just talking about rules that computers can use to communicate. Those rules are defined by specifications, and we'll reference several of those specifications as we dig into more specific protocols. And then each vendor is responsible for making code that aligns to those specifications. The idea being, if you follow the specification, then you can talk to others who also follow the specification. That's the whole idea. Now, those specifications can control a lot of different things. I have a few of them listed here. Things like connection initiation, so that's our greeting. Negotiation of connection characteristics. Some protocols provide optional features, and the initial connection initiation needs to communicate what those characteristics are and what's supported, so you can make sure that the packets are able to be interpreted. The data formatting, of course, one of the most important things is the actual structure the data is in, so the system knows what to expect and how to interpret that. So that's really important for encapsulation and decapsulation, which we'll talk about here in a moment. Things like error detection as well as connection termination. So again, not too different than a spoken language, the rules of spoken language. We have the rules of digital language or the rules of protocols.